Alright guys, welcome back. This is part 2 of example 1 for the 3-moment equation. Just picking up right where we left off, we had just calculated the internal and shears and end moments of each of these spans, and now what we want to do is we want to draw the shear force diagram and bending moment diagram and then solve for the reactions. So let's come up here and grab a picture of our original drawing. And let's come down here and we'll paste it and we'll get our shear force diagram and bending moment diagram set up. So first of all, before we get into looking at the information, because all of the stuff that we just calculated was for the stuff that's inside this span, basically from A to B and then from B to C, we do have this little bit hanging off the end here, but this is really easy for us to look at the shear. This is just going to be, there's just going to be a constant shear of minus 20 kilonewtons in this region if we look at it, right? If we took a virtual cut anywhere in this region from the end to A, we're going to see that we have 20 kilonewtons going down, and then there's going to have to be for the vertical force balance 20 kilonewtons of shear going up, and this is going to be basically opposite of our positive sign convention, which looks like this. Alright, so in this first region we get minus 20 kilonewtons, and let's just throw it on something like that, and we'll make that a nice straight line right out until we hit A, and we're going to label this as maybe I'll label it down here, minus 20 kilonewtons. Alright, and we can even label this, the whole diagram is in kilonewtons. Alright, so now we can talk about the information that we found for what's going on inside the span. We figured out that just on the far left-hand side of the this span number 1, that the internal shear was a positive 26.5625 kilonewtons. So that is basically just right up until, or just to the right of point A, basically. So that's going to be right about, let's say there. Let's connect these, and let's label this on. This is going to be positive 26.5625 kilonewtons. All right, so that's the shear there. We also know the shear just to on the right-hand side of the span, or just to the left of point B. Let's throw that on as well. We had that as negative 23.4375, and because we drew this in the positive sense and we got a negative value, that means that that is actually the negative value on the shear force diagram that we're seeing. So we have negative 23. Let's come down somewhere in about there. Okay, so knowing what we know about drawing shear force diagrams, in a region where there's no load, like no distributed load or anything, then it's going to be constant until we hit a point load. So that point load is right there. So this whole region is 26.562, whatever, over there. And this whole region is minus 23.4375. And it's not until we get this point load that we have the jump in the, maybe I'll try and draw that a little bit straighter, that we get this jump. And actually, if you look at this jump, it should be equal to the magnitude of the point load. And sure enough, if you have 26.5625 plus 23.4375, then those two added together are 50 kilonewtons. So that's a nice little check that this looks like we've done this correctly. All right, so if we inspect the other stuff that we did over here, we had VB2 is equal to positive 58.4375 kilonewtons. And so VB2 is the very left-hand side of this span, or just to the right of point B. It's positive value, and we drew it in the positive sense, so that means it is actually going to be positive on the shear force diagram. So we're going to come way up here, and this is going to be 58.4375 kilonewtons, and then down here at VC we hit negative 41.5625. So we can go in and throw that on as well. I think we might actually have to scroll down a little bit, make some room for this. So it'll be somewhere like that. This is going to be negative 41.5625 kilonewtons. All right, cool. So now what we do, again, throw on some straight lines here. That's going to be a jump up there. And then this, it actually should be decreasing linearly by 10 kilonewtons per meter. And actually, if you have 58.4375 minus 100, right, 10 times 10, that's going to bring you down to 41.5625. So that's pretty cool. That's a nice little check for us as well. All right, and then we'll just finish this up with a nice little line like that. All right, let's throw on some labels here just so we don't get lost. This was 5 meters long. This was also 5 meters. This section was also 5 meters. This section is not going to be equal to 5 meters exactly because these are two triangles across a span of 10. This triangle is higher than this triangle, and actually you can do similar triangles to find out that this distance in here is just going to be equal to 5.84375. Really, we end up just moving the decimal place over one because of these similar triangles, and then this one becomes, this base is 4.15625 meters. All right, so let's scroll down a little bit again and get our bending moment diagram set up. And now, as always, all we do is we take our areas here as our changes in magnitude as we go from left to right on the bending moment diagram. And where we have negative areas, it's going to be a negative change in magnitude. Where we have positive areas, it's going to be a positive change in magnitude as we're going from left to right. And the other thing is where we have straight lines here, horizontal lines, or constant values of shear, we get linear changes in the bending moment. And then where we have linear changes in shear, we're getting parabolic changes in the bending moment diagram. So we're going to need the areas of each of these, and they are here. And so we can get started now. So we know that the internal bending moment right at the free end should be 0 at the free end of that overhanging beam, and then it should also be 0 here at the end that we should be shooting for to line up with. So when we look at this first, we have a negative change in magnitude, and it's going to be, it's constant here, so it's going to be a linear change. So this is going to drop us down to negative 100. All right, so now if we go from negative 100 and we increase by this area, 132.8125 over this span, then we go up to a value that is, it's going to be about there or something, and this is 32.8125. Now if we take 31.8125 minus 117.1875, that's going to bring us down to a value of negative 84. It's going to be somewhere around here. Let's switch colors or switch things. So it's going to be negative 84.375. All right, now from this region to the next region, basically in line with this, we're going to be having parabolic change, and it's going to be by magnitude. So we have negative 84.375 plus 170.747, so it's going to bring us up to a value of 86.372. Let's see if I can draw this nicely. Yeah, there we go. And then this last area, we have to decrease parabolically because it's a negative area on that slope. And we have to decrease by 86.372, and boom, that brings us right down to 0, just like we were expecting. Awesome. The one other thing that we do want to check is, does this line up with the internal moments that we calculated earlier? Somewhere where we figured MC was 0, MA was negative 100, and MB was negative 84.375. So when we look at that, yeah, MA was negative 100 because this was in line with reaction A. MB was negative 84.375, perfect, right in line with that, and then we're ending at 0 for MC. So that's another nice little check that we can do to make sure that we've done this correctly. And the last thing that we want to do now is we just want to identify what the reactions are for AY, BY, and CY. Now we can get these right off the shear force diagram where we look at this jump in A. See, like where this point load is, what's pressing down, it's a magnitude of 50 kilonewtons, and the graph drops by 50 when we encounter that. Basically, if the point load is, if there's a point load pressing down, that's what happens. If there's a point load pressing up, the graph is going to jump like that. So if we just have minus 20, or if we have the magnitude here, 20 plus 26.5625, the sum of those two is actually going to be the magnitude of the reaction at A. So that is just going to be 46.5625. And because we should put in kilonewtons here while we're at it, and because the graph is jumping up as we go left to right, that indicates that it is oriented upwards, and that kind of makes sense. That's what we would kind of expect it when we're looking at this graph anyways, or the loaded structure. BY, same thing. We're jumping from negative 117.1875 up to 58.4375. So the sum of those two values, like the absolute value of those, is going to be 81.875 kilonewtons. Again, that's pressing up. And then when we look here at C, we're getting an internal shear of negative 41.5 right at the left-hand side of C. So if we draw a little virtual cut, here we have C, we have the internal shear is going down, right? It's opposite that negative sign convention. So it's going down with a magnitude of 41.5625, which means that the reaction here for the force balance in the y direction has to be 41.5625 going up, and that is our reaction at C. So 41.5625 kilonewtons going up. And then the last thing that you can also do to check is you can sum up these, and if you sum these up, you actually get 170 kilonewtons going up. And if we observe the the forces that are pressing down on the structure, we have 10 kilonewtons per meter times 10 meters. That's 100 kilonewtons pressing down, 50 and 20. So we have 170 kilonewtons pressing down on the structure. We have 170 kilonewtons pressing up on the structure. So it looks like we've done this right. All right, cool. So that's actually the answer to the problem. We got the reactions, we got the shear force diagram, we got the bending moment diagram, and this is definitely the way that I would recommend solving these types of problems. But if you're curious, you can come to the next video. It's part 3 of the same example, and I'm just going to solve for the reactions, shear force diagram, and bending moment diagram a slightly different way. It's more of like a graphical way, I guess, but just want to show you that there's another way to do this if you feel like learning how to do that as well.